I'm Larade, and I'm going to be going over an introduction to graph convolutional neural networks and a lot of the background theory surrounding it. When I was developing this talk, I ended up putting in a lot more background theory than graph convolutional neural networks, but I will be going over how you will encode data for a few different sorts of neural networks, including graph convolutional neural networks. But I'd like to begin this talk the way I began a lot of my machine learning talks, and that is by explaining what machine learning is and what machine learning isn't. So machine learning is, in short, a method of statistical modeling. So it is when statistics and computer science come together to attempt to find patterns inside of a data set and then use that data to construct a model which can predict events in the future, or it can predict people's behavior, or it can recognize objects inside of photographs or things like that. So it is a model that is built that we then use to apply to data that it's never seen before to gain some sort of insight about that data. However, machine learning is also not an incomprehensible black magic. We can understand how it works. And in principle, if we wanted to, we can sit down and dissect a lot of the models that we would end up building to try to figure out how exactly they work. Machine learning is also not correct every single time you build a model. There's a such thing as bias inside of a data set, and there's a such thing as bad models. A lot of the models that we're going to end up building are not going to be 100% correct all of the time, but they can be correct enough to be useful. It also isn't a magic bullet for every single problem that you're going to encounter in computer science. So it's not like Bitcoin. It won't completely revolutionize and fix everything all at once, but it is a very powerful tool to try to solve very specific sorts of problems. It's also not generalized artificial intelligence or the matrix. So it is not what you'd think of as an independent agent that can operate by itself and interact with the world. We're building very dumb machines to make predictions using data about the real world. And it's also not something you can plug into and upload your consciousness, although there is no shortage of matrices inside of machine learning. So before you begin working on a machine learning project, there's a few questions you should ask yourself. Specifically, what sort of data do you have? What would you like to predict? And can the data that you have accurately predict what you want to know? So as I said, it's statistical modeling, and we need to have enough data to be statistically significant. The data also needs to, in principle, be able to answer the question you're asking. So if you handed your data over to an expert that had an infinite amount of time to study it, could that person answer the question that you're attempting to ask? So if you're, the next sort of questions you'd want to ask is, how can you get your data into the model and how to get your insight back out of the model? A lot of what I'm going to be going over today is more or less answering this question just for specific sorts of data. Also, what parts of the data are important to the model? If we're using a raw data set, we may not necessarily want all of the information that's contained of it. And if we remove some of the information, we may actually be able to perform better than if we include all of it. The last two questions are more practical in nature, and these deal with what sort of tools you'll have and what sort of tools you'll need to build. There's a lot of frameworks that exist for doing machine learning, such as TensorFlow, PyTorch. Those are the two major ones. And there's also scikit-learn. So a lot of the time you should do a survey and see what tools already exist and what tools you'll need to build. Generally, when you're building something, it'll be things like a data loader or a data processor or something to integrate with the existing machine learning frameworks. Now, before I get into talking about neural networks in specific, I want to clear up a few bits of terminology. The first one is supervised learning. Now, there's two types of, well, broadly speaking, there's two types of machine learning. There's supervised and there's unsupervised machine learning. And in supervised learning, we give both the correct, what we believe to be the correct answers to the algorithm and the data that we expect it to train upon. So we give it the raw information, and we also give it what we believe to be the correct answers for that data. The reason why I say it's what we believe is because there can be bias in the data set. The data may not be any good, or the answers that we're looking at may not be correct if they're improperly prepared. So in supervised learning, you give the neural network the targets that you want it to attempt to predict. So you give it questions and answers, and it will attempt to find a route between those questions and the answers you provided. A weight is how indicative a factor is to a prediction. So the larger the magnitude of the weight, the more important that bit of information is to the prediction. And it can be indicative in a positive way or a negative way. So if we have some bit of data, then that means that X must or Y must be true or Y must be false. And we can use weights as a way to query and figure out what bits of data are important and what aren't. The last one I'd like to define on this slide is a function. So when I say function during this talk, I'm not referring to a computer function. So I'm not talking about a defined bit of code that you're working with. What I mean is the mathematical function, which is a relationship between two sets of numbers, X and Y, where for every X inside of the domain of the function, there is a Y according to some sort of formula. Also, when I'm going through this talk, I'm going to be introducing terms and then explaining what they mean slightly after they've been introduced. When a term has an asterisk on it, it means that I haven't defined it yet, but I will be defining it shortly. Just in case you see a word and you get confused as to what exactly it means, if there's an asterisk by it, it means that I haven't defined it and I am getting to it. Right. So the last bit of terminology I need to go over is over and underfitting. So overfitting or underfitting is when we have some sort of function. So the function is here in green. And we have a model that is too simplistic to accurately represent this function. So you can think about it as a student that hasn't really studied the material very well, and they're just making more or less educated guesses as to what they believe the answer is. The other way that fitting a model can go poorly is if we overfit the model. So again, we have the true function here, but the model contorts itself in all of these weird ways where it is too flexible and it will end up guessing the wrong answer because it has memorized the answer key and hasn't really learned any of the information that we expect it to. The sort of fit that we usually aim for is a true fit. So where the model approximates the function to a relatively good degree. And you can see here that the function and the model are not necessarily perfectly in agreement, but they're very close to one another. And again, with machine learning, we're looking for close enough. We aren't necessarily looking for 100% accurate all of the time. So to talk about training a neural network, it's very similar conceptually to teaching a math course. I've kind of been alluding to this metaphor as I've been going, but when you're training a model, what you're going to do is you're going to take your data set and you're going to split it into several different subsets. You're going to split it into a training set, a testing set, and a validation set. And these are analogous to the classwork and ungraded assignments that you give a student for the training set. The testing set is similar to assignments that you would be giving to a student so that you can get them back and grade them. And the validation set is your final exam for the course. It is the last thing that you do before you go into the real world and figure out if you know what you know or not. Now, when we're doing machine learning, or specifically supervised learning, the model will make predictions using the questions, so data, from the training set. The algorithm then compares its prediction to what the correct answers from the training set in order to measure the error in its predictions. So it will make a guess, and then it will begin to adjust its weights and biases in order to reduce the error using a backpropagation algorithm. And then it will repeat steps 2 through 4 until it's been terminated. Usually it's terminated by training for a certain number of iterations, when it stops improving, or when it's starting to get worse. So generally those are the 3 conditions that you'd end up terminating it. And then you'll check the machine learning machine learning algorithm one last time with the validation set to give it its final exam and make sure that it actually knows what it knows. So again, training set, very similar to classwork or ungraded assignments. Testing set is how you would assess it while it's being trained or assignments inside of the course. And validation set is how you test it after all of the training is done and you want to make sure it's going to work correctly before you deploy it to the real world. So the obvious question from this, though, is why are we splitting our data at all? Why don't we just throw 100% of the data at the model and see how well it does? And the reason why we can't do that is because it doesn't really reserve any of the data for us to test how well the model works. So the model may work really well in the data set, but then perform exceptionally poorly in real life. So this would be an example of an overfit model that has memorized the answer sheet and doesn't actually understand any of the math that you're supposed to be testing. And we can't train and test on the same data because the model will already know, so it will have already seen the correct answers and will be biased towards being able to answer those questions correctly. All right. So if there's any questions about this brief introduction or any terminology that I've glossed over, please either unmute yourself and ask your question or put it into the chat and I'll do my best to answer it. What we're all here to see, neural networks. So neural networks are composed of simple operations and weights that are applied to data both simultaneously and successively to extract patterns from the data. So if you've been studying neural networks for any length of time, you've probably seen a diagram that looks something similar to this. I've lifted this one from Neural Networks and Deep Learning by Michael A. Nielsen. It's the book that I read when I was learning about neural networks at the start of my process of learning this. I highly recommend the book, especially if you want to learn about backpropagation or any of the hard math that goes into doing neural networks. Now, we've seen this diagram before, but what I'm going to do is I'm going to take it and I'm going to break it down and go through the anatomy of a neural network and talk about a few of the different parts that are important in order for it to work. So the first of which is the neuron. Now, neurons are the internal components of neural networks. They will take in input values and output one out value. So what will happen is that the neurons will take in weighted inputs, apply a bias, and then output some number to the next neurons in the neural network. So in this example, it would take in all of these weights. So these weights over here, and then it will output its information to the neurons that it's connected to. And the bias is included to try to determine what the default behavior of the neuron is and help the neural network answer some specific problems, which I'll get into in a moment. So you might be wondering what sort of function neurons actually have. So it's usually a simple function that takes in a sum of weighted inputs, applies a bias, and then passes out the output information. And again, weight indicates how important an input is to a neuron, and biases indicate what the default output from a neuron will be. I'll go over this. So the sort of functions that we're looking at are very simple functions, specifically these functions. So we have three functions on this slide. It's probably hard to see a couple of them, but we have binary step in blue, we have the sigmoid function in red, and we have a tanh function in green. And these three functions are three of the simplest sorts of activation functions that you'll find inside of a neuron. They work as follows. The binary step function works by if an x is less than 0 going into a neuron, output a 0. If it's greater than 0, output a 1. Sigmoid function is a binary step function, but with a little bit of gray area in the middle. If you'd like to, you can look up the formula, but I won't necessarily be going over it right now. Sigmoid is a major upgrade over binary step for a few reasons. Specifically, this gray area allows modeling of more well, more gray area. And it also is differentiable, which ends up helping with our back propagation algorithm, which I'll go into in a moment. Sigmoid is very similar, or sorry, TNH is very similar to sigmoid, except it ranges from -1 to +1, which enables the neural network to capture more information. Right. So other activation functions which have become more popular recently are ReLUs, leaky ReLUs, and exponential linear units. Oh, sorry, I forgot to define what ReLU is. ReLU is rectified linear units, right? And leaky ReLUs are leaky rectified linear units, right? So in rectified linear units, if the number is less than 0, then output is 0. If the number is greater than 0, output that number. Likewise, leaky ReLUs are ReLUs, except they're divided, when it's negative, it's just the number divided by a large constant or the number. And exponential linear units are, again, the same as ReLUs in the positive space, but in the negative space, it asymptotically approaches -1. So, right. And these are generally the more modern neurons that are used in neural networks today. A lot of the previous slide have been relegated to very specific sorts of uses. So next, I'd like to demonstrate the effects of biases on neurons. So we can see here that there's three sigmoid activation functions, and they've all been shifted by a constant. So this is demonstrating how a bias would end up affecting whether a neuron will pass output or not. Because if the bias is -5, the neuron is less likely to pass an output. If it's +5, it's more likely to pass an output. And the reason why biases are important is because they can introduce more flexibility to the network and can help solve tricky problems. Specifically, it can solve the XOR problem, which is a specific kind of logic gate that is difficult to model without using neural networks. So, to recap, neurons are similar to logic gates that take in some number and output either a bool, so a 1 or a 0, or another number. And given enough neurons and a proper input, the neural network can assemble itself using backpropagation. Now, individually, neurons aren't very much use, but when they become many and when they become properly trained, they become a very flexible way to model phenomenon that are based on data. So the next part of the anatomy is the connection between neurons inside of the neural network. Now, these connections indicate which neurons are connected to which other neurons, and how they pass information through the neural network. The weight or the strength of the connection determines what sort of path is taken through the neural network, and therefore determines the output from the neural network. So if we have activations in specific inputs, different paths will be taken through the neural network, which will lead to different outputs. The next part of a neural network is layers. So layers are when we have neurons, or are drawn by having neurons that are stacked on top of one another inside of the diagram. And layons are groups of neurons that perform all of their operations at once. Generally speaking, the more layers and the more neurons you have in a neural network, the more flexible the neural network becomes, which means that it can fit more complex patterns. However, the more flexibility can often lead to overfitting, which again is when the student memorizes the answer key rather than understands the underlying patterns. Now, you've probably heard the term deep learning thrown around an awful lot if you've been in the machine learning space. And deep learning simply refers to when there are a lot of layers. There's no strict definition as to what deep learning is, but generally it's considered to be 4 or more layers of neural network. But it is kind of an arbitrary and squishy term. The last thing I'm going to go over in this brief review of anatomy is the loss function. And the loss function is the target that we set for the neural network to aim for. So we pick it as the user, and it is the error that we attempt to minimize. It's our metric for judging whether the neural network is getting better or worse as it continues to train. So it's kind of our eyes on what's happening inside of, or not so much inside, it's our eyes on how well the neural network is training and how well it's been doing. All right, so are there any questions about the anatomy of neural networks before I keep on going? The sort of neural network that I've been referring to is called a feed-forward neural network, and it's the simplest form of a neural network. So the signal is input from the data that's being processed, and the neural network performs rapid calculations to try to gain some insight and build a model from the data so that way we can get information on the other end of it. Now, the canonical example that I'm going to talk through on specifically feed-forward neural networks is the MNIST dataset. Now, the MNIST dataset is a series of digitized handwritten numbers that range between 0 and 9. Now, this is a sample of a 6 from that dataset, and these pixels have values between 0, so 0 for black, and 255 for the whitest of white. And how this information is encoded is that it is 784 integers that are fed into a neural network. And then on the other end of the neural network, there are 10 outputs that will output either a 0 or a 1, depending on which neuron or which number you're looking at. So in this example with the number 6, we would expect the 1, 2, 3, 4, 5, the 6th neuron. Well, it depends if we started counting at 0, but let's just say it's the 6th. So the 6th neuron will output a 1, and the rest of the neurons will output a 0. I'm going to talk through this in greater detail in a moment, just so that we can kind of observe how a neural network would end up working. We have a question of when should we have fully or partially connected neurons? That's kind of a complicated question. Generally, what we would end up doing is we would end up having a very densely connected densely connected meaning, let me step back for 1 second. Densely connected neural network. So if we have a network like this, where every neuron in this layer is connected to every neuron in this layer, that's referred to as a dense neural network. Generally, what we end up doing is we end up letting the backpropagation algorithm determine which connections drop to 0 and which connections are reinforced. Does that answer your question? So we don't generally want to be choosing whether or not a connection happens. Generally, we let the backpropagation algorithm handle that, unless you have a specific reason for trying to program it in such a way. Can I get a yes if that answers the question? Okay, cool. Right. So MNIST. The bias is, so let me go back. The bias is after the summation is done. So in this example, we would sum up all of the inputs and the weights, then add or subtract whatever bias we have. So it's inside of the neuron after all of the weights and inputs have been applied. Let me keep going. Are there any other questions? Does that answer that question? I don't understand what you mean when you say node. Right. So MNIST dataset. We have a large data set of handwritten numbers that are fed into a neural network. They are represented by a grid of pixels that range from 0 to 255. So we have 784 input integers, and then we output 10 Booleans. They're not strictly speaking Booleans. There's some number between 0 and 1, but when the neural network is trained properly, it should output a bunch of numbers that are close to 0 and one number that is close to 1. Again, with a sigmoid, it's difficult to get exactly a 1 or exactly a 0 just because there's so much gray area, but generally we would just round up after so many significant digits. So when we're training a neural network, the neural network will guess wrong during its first iteration. And then it will begin adjusting all of these weights and all of these biases in order to get itself closer to the correct answer. And depending on which nodes get an input, different pathways through the neural network are taken. To demonstrate this, I'm going to take the MNIST data set and I'm going to strip it down and talk through going through a neural network. So this is a neural network that takes in the image of a number that you would see on a digital clock. So we have the 7 lines that are inside of a digital clock, each one mapped to a neuron. And what will happen is each one of these neurons will pass information through the neural network, which will then output whatever number has been input into it. So to try to talk through this, I'm going to give a couple of concrete examples. The first one is the number 1. So if we have these 2 inputs lit up, what will happen is these 2 will pass signal to this layer of neurons. What will then happen is the neurons will arrange themselves in such a way that this neuron will output a 1 and all of the other ones will output a 0. So what will happen is we'll put in information into the 3 and the 6 input, because again, it's the number 1, so 3 and 6, pass that information to the internal layer, which will then output a 1 in this output and zeros in all of the rest of them. Now, if we have a different number, so say we have a 6, we'll end up putting in an input to all of these neurons, which will pass information to the internal layer, and then we'll output a 1 in the 6 category and zeros in all of the rest of them. And this is done using the backpropagation algorithm to adjust all of these weights to make sure that it can answer this question and this question at the same time. So the next obvious question is, well, what's going on the inside of a neural network? And the answer is that it's difficult to tell. So in principle, we could sit down and we could map each individual input pixel to some sort of output and figure out how indicative each pixel is to whatever prediction you're looking at. Now, in practice, this is very difficult. Just because it's time consuming to test all of the 784 inputs and see how each of them ends up working. Right. So once the signal begins being processed, it is called the latent space. And it's an intermediate step that's inside of the neural network that is, generally speaking, meaningless to us as human observers. So it's a compressed and partially processed signal coming from the data that is very similar to our nervous system. So we can see that it's passing through. However, trying to understand exactly what's going on ends up being very difficult in practice. Right. So I'd like to open up the floor to questions really quickly before I move on to the next topic. When we are going through and we're adding inputs to a neural network, the fact that specific inputs are lit up or not lit up will end up having different weights and different biases towards different outputs. So if this 3 cell is lit up, it will be weighted negatively towards 6. So it will end up having less, what's the word I'm looking for? It will end up negatively weighting this bit of information towards a 6 because 6 does not contain this bit of information. I don't think I explained that properly. Likewise, if there's a 2 or a 5, we can automatically eliminate number 1 or number 3 from when the network is training. It will automatically set up weights to make sure that 1 and 3 don't light up when 2 and 5 are lit up. Does that make sense? If that makes sense, please put up a yes in chat. If it doesn't, please put up a go slower and I'll go over it again. I've kind of alluded to this point a couple times, but inside of neural networks, it's very important, or inside of machine learning in general, it's very important that we have a robust set of data. And the reason being is that if we have poor data, so data that is off-centered, or data where some of it's been cut off, or just noisy data, what we need to do is we need to have enough data so that way our statistical model can be reliable. If you cast your mind back to your stats course, you need to have a certain amount of data before you become statistically significant. And that's kind of what we're aiming for when we're doing neural networks. So I'm going to start talking about the backpropagation algorithm in a moment. But first, I want to cover a concept called gradient descent. And gradient descent is an algorithm that will attempt to find minimum or maximum, or minimum values inside of a function by following its derivative. So if we have some function, so this is just a function that I just pulled out of the air, we can see that there are two minimums inside of this function. There's a global minimum and there's a local minimum. And what we can do is we can use a gradient descent algorithm to follow this curve and attempt to find a minimum. Now, depending on where we start on this curve, we aren't necessarily going to get to the global minimum of the curve. So if we start, for example, here, then we're going to descend into this trough. However, if we start here, we're going to descend into this trough. There's some weird interactions you can get where if you start on a very steep slope, you can bump over and land into the wrong minimum. But that's something that you could read about if you had any interest in the gradient descent algorithms. Now, the way that we do this in practice is that we will attempt to approximate this function using the derivative. So the green function is the derivative of the blue function. And what we can do is we can take 2 points on the blue function, and we can see which direction the curve is going, and then take a step in that direction to attempt to find the minimum. Now, how this relates to backpropagation is that backpropagation is effectively a gradient descent where the parameter being descended is the loss function or the measure of error that we've defined for the neural network. So we have all of our weights and all of our biases, which determine how correct the neural network is. And then what we do is we measure the error in that prediction, and then we adjust all of the weights according to this backpropagation algorithm. Again, if you'd like to read more about backpropagation, I highly recommend that you read the Nielsen book. Now, this is conceptually similar to tuning in an old-fashioned radio, where you can tell when you're getting close to the frequency, but you can't tell where the exact frequency that you need to be on is. And again, this is one of the things with machine learning where we are aiming for close enough. We don't need to be directly on target every single time. We just need to be accurate enough to be useful. And yeah, the loss function is whatever measure of error you care about. It could be mean absolute error, it could be mean squared error, it could be any number of different metrics. And again, it's done using partial derivatives to determine how each weight should be adjusted. Now, specifically with the backpropagation algorithm, the more neurons we have in a neural network, the more demanding the optimization becomes. So when we add neurons to a neural network, we increase the number of parameters proportional to the number of connections that we have inside of a neural network. So if we introduce more layers or more neurons, it ends up taking a lot more computational time in order to arrive at an optimized model. And also, just a note before I move off this topic, backpropagation works slightly different in each different sort of neural network architecture I'm going to be going over. Generally, it's adaptations that are done to address specific sorts of problems, but when you're beginning to work on neural networks yourself, take a moment to read through and make sure that you understand how the backpropagation algorithm applies to each different sort of neural network that you're going to be using. Right. So when we have our data, and we have our model. The questions, it's called backpropagation. Well, I'm actually not really sure why it's called backpropagation. I believe there's an explanation in the Nielsen book, but I'm not 100% sure why it's called that. The procedure for direction and step size and gradient descent. So inside of neural networks specifically, backpropagation takes smaller steps as the neural network keeps on going. There's a parameter that's known as the learning rate, which basically determines, give me one sec, it's easier if I have a visual aid. There's a, what's what I'm looking for? There's a parameter called the learning rate, which basically determines how big of a step you're allowed to take when you're doing the gradient descent. So generally, when we are training a neural network, we have the learning rate decrease as we are training the network. So when we start, we want the learning rate to be large because we assume that we are far away from the optimal arrangement of the neural network. However, as we get closer to the optimal arrangement, the steps generally become smaller. Does that answer your question? I'm not sure what jitter is. If we're stuck in one of the local minimum, if we're stuck in a local minimum, generally we're not even sure we're stuck in a local minimum. Generally, so when we're doing the backpropagation algorithm, or when we're doing our gradient descent or a backpropagation algorithm, we want to find the global minimum, but there's no guarantee that we will. Generally, the way that we try to overcome this is by training multiple models. Nielsen, if you could explain what jitter what you mean by jitter, I'm not exactly sure. Data and data processing. When picking a model for machine learning, generally we want to ask the question, how are we going to get the data into the neural network in a form that the neural network can understand and use? So in order to get the data into a neural network, the data needs to be processed. And I like to think of this as being conceptually similar to taking a massive log and trying to thickness plane and cut and refine down to something that is very usable and smooth that we can work with. And most of the rest of this talk will cover ways that neural networks can interact with data and little ways to help with data preparation. So specifically talking about sequence data, image data, and graph data, and how to get those into the neural network. So before I keep on going, one more statistics concept that I'd like to go over. So a problem in statistics is the concept of signal to noise ratio. So not necessarily all of the information is necessarily useful to the agent that is doing training or predictions. So what we need is ways of stripping noise out for the neural network, so that way we allow the signal to propagate. Now, to demonstrate signal to noise ratio, I'd like you to do an exercise with me. So I'd like for you to think that you are playing some sort of online video game, or you're in a video call, and there's somebody that's trying to get information to you. It might be information like the enemy has a health station up ahead, or there's a trap for us up ahead, or something like that, where you need to get this information so that way you can make an informed decision about what you're going to do next. There may also be signal for somebody else. So say you're playing a character that can't heal and somebody on your team is asking for healing. That signal is just not signal for you. So you're not necessarily that interested in it. Now, the concept of noise enters in when we have things like music or somebody on the microphone that won't stop talking about whatever, or somebody on the microphone that's getting very angry. And you can see that as more information goes through, there is this loss of the signal to a lot of the noise. And what we want to do is we want to make sure that we can strip out a decent amount of the noise and allow the signal to propagate through the neural network and then gain some sort of insight from it. So the first variant of neural networks that I'd like to talk about is recurrent neural networks. And these are used for sequence data processing. They have feedback loops built in their structure where a layer will pass output to itself or a previous layer. And it's very similar to this sort of architecture where we have inputs going in, the information traveling through the neural network, and an output surface to the user. However, some sample of the latent space is taken and put back into the neural network as an input. And this is done to try to retain information in a stream of data. So if I'm speaking, well, I am speaking, but if somebody is speaking to you, the order of the words that they're saying is very important to the context of the sentence and the content of the sentence. So, right. And this sort of architecture is effectively the same as having a neural network that feeds back into itself and continues to propagate forward as it goes. However, this creates a very specific sort of problem known as the vanishing gradient problem. So if we input the first word of our sentence into a neural network and it gets processed, that entire signal passes through the neural network. However, without specific sorts of architecture inside of the recurrent neural network, the signal from the first word gets diluted as more words pass through the neural network. And this is known as the vanishing gradient problem. Now, to demonstrate, oh, sorry, I moved on to the next topic without asking for questions. Were there questions about the, wait, no, I already did the questions. Sorry. Right, so this presents a problem where we have, as the sentence goes forward, whatever the first word in the sentence ends up becoming less and less remembered by the recurrent neural network. So if we have a few example sentences that will demonstrate this problem, we can show that if the first half of the sentence can be more indicative to the meaning of the sentence than the last few words in a sentence, and this creates problems for us. So if we have these three sentences, all the neural network is likely to pick up is the last couple of words and then the words try again, because all of these sentences have been artificially constructed to end in the same way. So if we say, don't do that right now, that means something very different than fix that or don't try again. And what we need to do is we need to have some sort of way to remove information that is less relevant while retaining the information that is more relevant. So again, the concept of signal to noise ratio, we need to take the noise, sort it out, and then retain the signal. And one of the ways to do that is by getting rid of specific small little words inside of a sentence and by retaining the words that are important. And this is done by using things such as long short-term memory cells and gated recurrent unit cells. Now, these are adaptations for recurrent neural networks that implement specific sorts of structures which can help capture more information and also forget more information. So we can take the tiny little words that are mostly there for grammar and for humans, remove them, and then retain more of the signal that's passing through the network. Now, in the interest of time, I'll be going over how LSTMs work only, but GRUs work off of a similar principle. In general, when you're training a neural network, you want to try both long short-term memory units and gated recurrent units, just to make sure that you are giving both of them a decent chance, because sometimes one will work better than the other, and sometimes the other will work better than one. So to go over the anatomy of one of these long short-term memory units, let's take one and we will again pull this apart and talk about all of the individual parts of it. So the first part is the cell state, and this is the information as it's passing through the neural network. So this is the memory of what has come before, and well, yeah, it's a memory of what's come before. Now, I want to draw your attention before I start talking about the ways that the neural network interacts with the cell state. Specifically, I'd like to draw your attention to these neurons down here. So the sigma is for sigmoid neurons, and the tanh is for tanh neurons. And to refresh your memory, sigmoid neurons are the neurons that go between 0 and 1. Oh, sorry. Sigmoids are between 0 and 1. I was pointing to binary step, my bad. And tanh goes between -1 and +1. And what we can use is this specific sort of neuron function in order to update and change our cell state. So the first gate and the leftmost gate on this diagram is called the forget gate. And what the forget gate does is that it will tell the neural network whether or not to clear out the cell state. So if there's a new sentence, or if there's a change in the subject of the sentence, or something like that, the forget gate will tell the cell state to discard the information that it is retaining. Right. So this is done using the sigmoid neuron, where if it outputs a 0, we do matrix multiplication and remove that information from the cell state. So it can sigmoid neuron can enter a number between 0 and +1, or, well, yeah, a number in between, and it will determine how much of the cell state to retain or how much of the cell state to forget. The next gate that I'd like to talk about is the input gate. Now, the input gate is how we add information into the cell state. So this is consisting of a tanh, so between -1 and +1, and a sigmoid neuron, which goes between 0 and 1. And what the sigmoid neuron does is that it gatekeeps what information gets added into the tanh, or added into the cell state. So the sigmoid neuron will, if it's a 0, eliminate the signal from the tanh neuron. And if it's a 1, it will allow all of the signal to go through. This is generally useful for things that are like those little words that are just there for grammatical reasons, or information that's not terribly important to this LSTM gate. Generally, when we're working inside of a recurrent neural network, we have several LSTM gates that are all operating on different parts of the data and care about different things. But right, so this is how we process the information that's coming through and determine whether or not to add it into our cell state or not. The last thing that we do is the output gate. So again, we have a sigmoid neuron that will either tell the network to output information or to not output information, or to output some of the information. And what we do is we take the cell state and we multiply by the sigmoid neuron and output some information to the user. Okay. Does anybody have any questions? I'm going to start reviewing, and if people have questions, please start entering them into the chat and I will answer them when I'm done the review. So the structure of LSTMs and GRUs enables the neural network to reset itself and also ignore some of the information that's coming through in the stream of data. So these two features enable the network to screen out unimportant data, thus improving the loss of signal as we progress through the neural network. It also improves our signal to noise ratio by stripping out a lot of unnecessary information or noise from the predictions. Generally speaking, when we're working with LSTMs or GRUs, we want to use several hundred of them to capture different interactions in whatever stream of data we're working on. All right, does anybody have any questions before I move on?
Yes, I was wondering, are those sigma functions?
Questions on LSTMs before I keep on going? I haven't gone over GRUs because, again, GRUs and LSTMs are two ways to try to get the same sort of information. And generally, you'd want to try both if you're building a neural network for production. So the next sort of neural network I want to talk about is convolutional neural networks. Now, convolutional neural networks tend to be used for image or video analysis, and they employ machine learned filters to try to reduce the amount of information going through the neural network. So the first layer in convolutional neural networks is designed to reduce the complexity and remove a lot of signal and even more noise, so that way the neural network can have a manageable amount of data to work with. And the reason why this is necessary is because a lot of images contain a lot of information that we don't necessarily care about. So if we look at this image here, we can see where our neural network has drawn bounding boxes around a bicycle, a guy, a truck, a few cars, and we need to be able to remove a lot of this information that is more or less wasted space in the image. So that way the neural network can focus on what's important and actually make decisions as to what it's looking at. Now, you can think about times in your own life where you've had tunnel vision and you haven't been capable of seeing something that is fairly obvious after you take a second to slow down and look at it again. Our nervous system kind of does this automatically, where if you can think about, if you're watching something, your eyes are going to be drawn to motion, your eyes are going to be drawn to bright colors. And what we're trying to do is recreate that for the neural network, so that way it can do its job more easily. And just to give a quick little example, you might remember this scene from Star Wars where all of these aliens are cheering. But something you may not have noticed, even though it's very obvious in the frame, is that E.T. makes a cameo in this image. So you can see where you would need, you yourself throw away a lot of information in the images that you're looking at. And we want to help the neural network do that, so that way it can figure out what's important and give us some sort of insight. So to quantify the amount of data that's inside of an image, we're going to take a small photograph. So what I'm saying is look at this photograph so I can explain how much information is inside of it. So we have 720 pixels by 900 pixels, which gives us 648,000 pixels, which is far too many neurons to be feasible, especially if we consider that we might want to have, well, we do need to have multiple layers in order to process the information. So this is why we need to have convolutional neural networks, is because if you're going to back propagate across 60 or 648,000 variables, you're going to have an awful lot of math, and it doesn't matter how many GPUs you throw at that problem, it's going to take forever to get it done. So, right. Before I keep going, I'd like to define what a convolution is in terms of mathematics. And it's where two functions overlap with one another and we combine them. So we have two functions, f and g, and we combine them using this transformation. And the function that results from the convolution is the overlap over a given range. For convolutional layers inside of a neural network, though, there's a few different sorts that we tend to employ. This is in no way an exhaustive list. And if you're going to be processing your own image data to build a convolutional net, I highly recommend that you read about different sorts of convolutional filters that are available and how they end up processing and transforming your image. But to give you a brief introduction, we have pooling layers, which are similar to compressing an image. So before we end up working with an image, the neural network will compress it down and attempt to just reduce the amount of data that it's working with. There's also edge detection, which is useful for if you're trying to pick objects out of a background. So if you remember the picture of the bounding boxes that I showed earlier, that would be a useful example of when you'd want to use edge detection. There's also sharpening and blurring, which can be useful if you have images that are particularly noisy or there's a lot going on in them, or if the background is particularly detailed or things like that. So to go over and talk about how a pooling layer works, just to give you an example of the sort of transformations we're looking at, I'm going to talk about it using a crudely drawn picture of an umbrella. So this is something that I've kind of come up with as a way to demonstrate and talk through how a pooling filter actually ends up working. So we take this image, crudely drawn picture of an umbrella, and we encode it the same way we would in the MNIST data set. So we take these pixels, these have a color saturation value between 0 and 255, and that's how we would represent the image to the neural network. So take that, and we would apply a pooling filter to it. And the way an average pooling filter works, so there's a few different types of pooling filter. There's an average pooling filter, there's a max pooling filter, and oh my goodness, it's slipped my memory what the other kinds are called. But when we're working with a pooling filter, the way that it works is that you will take some grid of numbers. Generally, it's a 3x3 grid, and you will take the average or the maximum of that grid of numbers and then put it onto a new grid of numbers. So what we're doing is we're taking this information, we are taking 9 cells of information, and we are converting it down into 1 cell. And what this does is that, again, reduces the amount of information in the image, so that way the neural network can even process it. And then we go along and we do this for all of the sets of 9 numbers in the image. And eventually we're left with some representation that looks something like this. And what this would map onto is a compressed, crudely drawn picture of an umbrella. And the reason why we do this in real neural networks is because the images are much larger than, what is this, a 7x7 of an umbrella. Usually we'd end up having several thousand pixels to work with, but where we only have 49, it ends up being really, really janky after it gets compressed. But it's a way to take the information that we have, strategically throw out a decent amount of the information, and get left with some compressed representation of what we're looking at. So the purpose of convolutional layers is to attempt to remove most of the noise and some of the signal, then break down the data so that the neural network has a workable amount of data to use. And convolutions are similar in purpose. Well, at least, sorry, I should rephrase this. Pooling filters are similar to compression, are similar to lossy compression algorithms. The edge detection and the edge detection, blurring, and sharpening algorithms are very similar, except instead of taking 9 numbers and producing 1 number, you take a central number and adjust all of the other numbers. Right. So does anybody have any questions about convolutional neural networks before we keep on going? I'm not, okay, so somebody asked me if you can add a Fourier analysis to the image as a means of compression. I believe that there are some Fourier transforms that happen in convolutional neural networks. I'm not 100% sure what they're used for, but I have heard of Fourier transforms and that sort of transformation being used inside of convolutional neural networks in order to try to do something. I'm not 100% sure. I absolutely by no means know everything about convolutional neural networks or neural networks in general. I highly suggest that if you have really specific questions, either ask me and I will attempt to find the answer, or check for some peer-reviewed literature about applying specific sorts of transformations to the data that you're looking at. And yeah, convolutions are like filtering. They're a way of trying to strip out what's not important and retain what is important. Any other questions about convolutional nets before I keep on going? Okay, so the next portion I'd like to talk about is mathematical graphs. So mathematical graphs are a way of tabulating how different entities interact with one another. So if we have a very simple graph of the game of rock, paper, scissors, the way that it works is that we have nodes in our graph, which would be analogous to hands that you can throw in rock, paper, scissors. And we also have edges, which is how each different play that you can make in the game interacts with the other plays that you can make. So in rock, paper, scissors, if you're unfamiliar with it, the way it works is that you will count to 3 and then you will play out a hand symbol. And whatever hand symbol you play will beat another hand symbol, tie with itself, or lose to a different hand symbol. So rock beats paper, or sorry, rock beats scissors, scissors beats paper, paper beats rock. And the edges in this node are how different nodes interact. And we can tabulate this in the form of a matrix. So we have a very simple matrix for how rock, paper, scissors ends up playing out. So if you play rock against rock, 0. Nothing happens, you play again. Play rock against paper, you lose a point, your opponent gains a point. If you play rock against scissors, you end up getting 1 point for yourself, and your opponent ends up losing a point. And this is an example of a directed graph. So in a directed graph, A interacts with B differently than B interacts with A. An undirected graph would be something like if we have a chemical bond between two identical atoms. So if we have a carbon bonded to a carbon, that would be an example of an undirected graph because A and B interact symmetrically with one another. So to give a couple of concrete examples of graphs, it could be something like a social network. So how different people get along with one another and how they end up interacting. It could also be something like a molecule where we have nodes in the form, oh, sorry, let me talk through this example a bit more. So we have a social network where we have nodes, which are the characters, and we have interaction or edges, which are the interactions between the characters. In an example of a molecule, we have nodes, which are the atoms inside of the molecule, and edges, which are the interactions between the molecules. The graph that I expect most people to be most familiar with, though, is the graph of Pokemon weaknesses and strengths. And I kind of put this in as a joke when I was first making this talk, but it actually ends up being a fairly interesting graph to take a look at, because there's a bunch of different ways that they can interact with one another. And there's a bunch of different ways that, and it's also a directed graph where fire interacts with water differently than water interacts with fire. Now, for those of you that aren't super familiar with the way Pokemon ends up working, is you have these little monsters that are given a specific type, and based on what they are fighting against, they get an advantage or a disadvantage depending on this graph. Right. So I'm going to be using this graph going forward as a way to try to process and encode a graph to work inside of a neural network. The reason why we would do this, however, is if we wanted to try to find some information out about a graph that is not readily teased out of it. Recently, this sort of neural network has been used extensively for screening drug-like molecules. So what you will do is you will encode a lot of molecules that are drugs into a neural network and then train on those graphs and attempt to figure out what sort of drug score or what score a molecule would have for being a likely candidate to be a drug. So we would have known drugs and we would give them a high, what's the word I'm looking for? We would give them a high score, and then what we would do is we would give the model unknown molecules and then see how well those score according to the neural network. Likewise, you can do it with social interactions where you can see how likely it is two people are going to get along if they've never interacted before based on the social circles that they're in. Right. So in order to encode a graph into a neural network, the first thing that we need to do is we need to convert it over into an adjacency matrix. So I've cut out normal from this graph in order to try to encode how more interesting types end up interacting. So if we have fire attacking fire, it ends up being multiplied by 1/2. If we have fire attacking water, it gets multiplied by 1/2 again. Fire against wood gets a 2 times bonus, and fire against electricity gets a one-time bonus. And this is just simply how the different nodes inside, or the different types inside of the game, interact with one another when they're attacking or defending one another. So we have this representation, and since we've all been watching, we will look at this and say, okay, well, this is a matrix of information, and we should just be able to throw this into the neural network and have it come up with some sort of information, because all of the information that we've been working with so far has been just matrices of numbers. However, there's a specific problem that occurs in graphs. And this is that if we shift the position of things inside of a graph, the same information is retained. So if we have fire and we move it down lower into the graph, the information contained in the graph is the same as the, well, sorry, let me rephrase this. If we take the order of the agent of the, sorry, if we take the order of the entities in our graph and we shuffle them, the contents of the graph doesn't actually change, because all that we care about in the graph is how different agents interact with different agents. So if we shuffle the order is completely arbitrary. So what we need to do is we need to find a way to condense this information into something that a neural network can work with. And to explain this, I'm going to walk through how we would encode the Pokemon matrix into a graph convolutional neural network to try to determine some insight about the way the types interact with one another. Now, before I even get started, there's a few issues with working with this graph. The first of which is that the graph is nearly maximally connected, which will end up presenting issues if we, when we start condensing our information. Generally, if a graph is not maximally connected, we can end up condensing a lot less information because there's a lot less interactions. Also, the features that I'm going to engineer for this graph are going to depend on the edges, which, to my understanding, means that it's going to, it's not going to work as well as otherwise. But again, this is just for the purposes of demonstration on how somebody could encode graphical information into a neural network. And the last issue is that we're going to train and test on all of the data if we were going to do this for real. So realistically, we couldn't actually test and see how well this model was working. But for the purposes of demonstration, I'm going to go over this quick little example. Maximally connected means that everything interacts with everything. Sorry, I kind of glossed over that term. So maximal connection would be if we had a graph of people, say we had 20 people and everybody knew everybody in that group of people. A not maximally connected graph would be if we had 20 people and say everybody knew 4 or 5 people in the room. So rather than have an interaction with everybody, you have an interaction with a few people, if that makes any sense whatsoever. Okay. So if we encode one Pokemon type for our vector, so we have, I'm just going to take fire because it's the first one that's interesting to work with. And we can condense this information into some sort of aggregation, which is done by collecting the attributes and then aggregating all of them together. So in this example, we have a lot of ones, a couple 1/2s, and some double damages. So what we will do is we'll condense this all into one number. So that way what we can do is we have some representation of how fire interacts with every other type when it's attacking. And we can do this for both attacking and defending, and we will generate features that look something like this. So these are the features that we will pass to the other nodes when we're working and trying to train our neural network. So what we do, we take these aggregations and we give them to the neural network, creating a vector representation for the node. So each node is given these two numbers based on their attacking and defending stats. And theoretically, what we could do is we could come up with statistics like how well is a type represented, what are the moves that a type has, and things like that. However, to keep this example simple, I've only just worried about the attacking and defending attacking and defending statistics. Now, in order to make sure that this works correctly, we need to have different ways of treating different sorts of interactions. So where in this example, we don't differentiate between different types, there's 4 different types of interactions we can have. So let me go back and pull up the chart. Well, okay. So there's 4 different ways that types can interact with each other. There's a 1x multiplier, a 1/2 multiplier, a 2x multiplier, and a times 0 multiplier. And each different type of interaction is given a different weighting matrix. So if we have a type interacting with a type multiplied by 1, that will be given a specific weight matrix when it is when the information is passed through the graph. So we are querying something about a node in the graph, and we aggregate all of this information, pass it through a weighting matrix, and then that is given to help answer the question that we're asking of the graph. Right. So, and we have one weight matrix for each different type of interaction. So if we have type 1 interacts with type 2 by a 1x multiplier, that gets its own weighting matrix. Same as type interacting with another type by 1/2 is given a different weight matrix from a 1x multiplier. Likewise, 2x multiplier is different from the other 2, and a 0x multiplier is different from the other 3. And this is done in a way to try to have different interactions weighted differently when we are processing the data through the neural network. Also, if we differentiated the types that we're working with, so say we had types A, B, and C, we would have one for type A interacting 1/2 with type B, type 1 interacting with 1/2 with type C, and for all of the combinations that we could possibly have for nodes, types of nodes, and types of interaction, and types of node. So if we have a few different types of nodes, there is a different weighting matrix for each pairing that interacts in a specific sort of way. Generally, the example that's used is users and tweets. So if a user likes a tweet, that's a sort of interaction. If a user reports a tweet, that's an interaction. If a user follows a user, that's a sort of interaction. And each one of these will be given a different weight inside of the neural network. Also, these weights are determined via I believe it's the backpropagation algorithm again. Right. So the last hurdle that we have with this specific example is that we need to have what our goals and our error measure is. And this is where this example in particular breaks down really hard. But in principle, we could invent a new Pokemon type and then just attempt to run it through the algorithm to determine how numerically fair it is to the balance of the game, and whether or not we should add in that new type if we were, say, making our own rip-off of Pokemon or something like that. All right. So is there any questions about graph convolutional neural networks, or why and where you'd like to use them? Or if there's any questions about some information that I didn't cover, but people have questions about. Well, while people are typing out questions, I'm going to go back and I'm going to talk about dropout. So somebody was asking, I can't remember exactly who, was asking about jittering the data, or so effectively, to my understanding, jittering the data, the way you refer to it, is selectively introducing noise in both directions so that way you can make the model more robust. Please correct me if that's not what you mean, but that is something that is starting to be looked at a bit more often. If you've noticed when you're doing okay, so machine learning secret, CAPTCHAs are for training neural networks. So whenever you log into a website and it asks you to fill out a CAPTCHA, that's what it's trying to do. And that's why a lot of the CAPTCHAs that you've been seeing lately end up having effectively a noise filter passed over them, where you can see that the image is grainy and a bit distorted and a bit like it's coming through. If you remember an old TV back when the signal used to suck, if it looks like that, that's what they're trying to do, is introduce noise to the training data so that way they can improve their models. It's a selective injection of noise, because if there's a certain, what's what I'm looking for? There's kind of a joke in neural networks called the strategic pixel attack, which is where if you Google it, it's where you put one pixel off on a neural network, and the neural network gets completely and hopelessly confused and has no idea what it's looking at. Right. So yeah, jittering is being used. I just hadn't heard that term before. Right. Dropout specifically, I mentioned that earlier. It's when you have a neural network. So let me just pull up a diagram of the neural network real quick. Let's see. So if we have a neural network, it's basically saying, okay, for this training iteration, can I change the color of that? I wonder. So for this training iteration, I want this neuron to not exist. Ooh, oops. Oh dear. Okay, anyway, I don't want this neuron to be used this time. So I want you to artificially remove this neuron for a specific training example, just to see how well we do without it. And it's effectively a way of trying to train, or it's effectively training a bunch of different architectures, not at once, but it's a process of trying out a bunch of the possibility space. And also it ends up solving a problem where we end up having one, for lack of a better way of putting it, we have one loudmouth neuron that is doing all of the deciding, and the rest of the neurons are too quiet to have any contribution to the final answer that's given from the neural network. Right, so I said I'd talk about that, so let's go back to where we were. All right, so does anybody have any questions about anything that I've been talking about, or anything with relates to machine learning or anything like that?